Welcome to Math with Mr. Bill. I'm Bill Anderson, and today we're going to be working on problems involving implicit differentiation. So we have here a word problem. A large pile of sand grows as sand is deposited on it. The height and the radius are always the same as it grows. The height grows at a rate of 2 feet per day. How fast is the volume changing when the pile of sand is 7 feet high? So when we want to work with an implicit differentiation problem, we're going to be working with a geometric formula or an equation that has a lot of different variables in it. Could be 2 or 3, could be several, but that at least one of those variables is in terms of another one of the variables in the expression, in the equation, or all of the variables are in terms of one particular variable, as we'll see in this one here. Let's first draw a picture. So here we've got our cone, and the cone is going to have a height and a radius. So our height here, comes down from the vertex all the way to the center of the circle, and then the radius goes out from the edge of the circle or from the center of the circle to the edge of the circle. So this is H right here, and then this line right here is R. Okay, and what does it tell us? It tells us that the height and the radius are always the same. So that means that H is equal to R. It also says that the height grows at a rate of 2 feet per day. And since we're talking about a rate, we can turn that into a differential. And so we can say that the derivative of H with respect to the time, we can say the number of days, but we'll say the time is equal to 2 feet per day. Okay, so now we want to find out how fast the volume is changing. So we're asked, when we talk about volume changing, that's also a derivative. Anytime you talk about a rate or how fast something's changing, that's going to be a derivative. So we're asking, what is dv dt when h is equal to 7? Well, now we need to know what the volume is. And so what are we talking about? We're talking about the cone, and so we need to know what the volume of a cone is. So the volume of a cone is equal to 1/3 pi times the radius squared times the height. So when you look at this problem, you notice that we've got 3 different variables. We've got our volume, we've got our radius, and we've got our height. So as the volume changes, what else is changing? Is both the radius and the height changing? Well, the problem, it says so. It says that both the radius and the height are changing as the volume is changing. So that means that each one of these variables changes with respect to time. So V, R, and H all change with respect to time. That means we can take the time derivative of this equation. So that's what we're going to do. We're going to find the time derivative of the volume of a cone. In other words, we're going to take dd dt of this entire equation. Now, both r and h are functions of time. That means when we take the derivative of r squared times h, we're going to be using the product rule. So let's step through this here. So we've got the derivative of the volume with respect to time is equal to the derivative with respect to time of 1/3 pi r squared h. The 1/3 pi is just a constant, and that can actually come out front of the derivative. And I'm going to rewrite it as pi over 3. And then we're going to be finding the derivative with respect to time of r squared times h. So that's going to require the product rule. So to take the derivative of that, so do a little side work here. That's equal to the derivative of the first, so 2r. But because we're not taking the derivative with respect to r, we're taking it with respect to t, we also have to put on the derivative of r with respect to t times h plus the first times the derivative of h, which again, we're not taking the derivative with respect to h, we're taking it with respect to time, which means that we're going to take the derivative of h with respect to time. So there's the derivative. Now let's go ahead and put everything back in here. So we have dv dt equals pi over 3 times 2r dr dt times h plus r squared times dh dt. So now we need to get all of these pieces, because what we're looking for is dv dt. Remember that. So we need to find an r, a dr dt, an h, and a dh dt. So looking back up at the problem, we see a few different things. We know what the height is 7. That means the radius is also 7. It says that dh dt, the change of the height with respect to time, is 2 feet per day. And then we got to figure out what dr dt is. Well, if h is equal to r, then the change of the height is going to be the same as the change of the radius. And so the change of the radius is also going to be 2 feet per day. And you can actually show that to yourself if you want. You can say, well, h is equal to r, and then you take the time derivative of both sides. And then that turns out to be exactly what we want. dh dt equals dr dt. All right, so now let's put everything into our equation. So dv dt is equal to pi over 3 times 2 times 7 times dr dt, which is 2, times h, which is 7, plus r squared, so that's 7 squared, times dh dt, which is 2. So combining all of our pieces, we get 2 times 7 times 2 times 7, which is 196, plus 49 times 2, which is 98. So that it's going to be equal to pi over 3 times 294, which is equal to 98 pi, and you multiply it by the pi over 3. So our change in volume with respect to time is equal to 98 pi, and the units here are cubic feet per day, since volume is in terms of feet or cubic feet. And that should do it. Thanks, and I'll see you in the next video.